Hello everyone, I hope you're all doing well. So in today's video, we are going to go through the 2019 Specialist Maths Exam 2. I remember doing this exam, of course with my students, and I'm not going to lie, this is one of the most hardest exam that I've ever seen. Like, I remember doing it, I've done it like 3 times, of course, with past students and stuff. I'm used to it, but it's one of the most hardest. I don't know what VCA for putting this rubbish in here. Generally, yeah, it's a really, really hard exam. So I want to just, here are my suggested solutions. If you are struggling with this exam, please watch these suggested solutions, learn from it. I'm going to try to explain everything really, really simply and try to break everything down. I hope this video finds you well, and yeah. And just like always, guys, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. Let's smash through this video. Alright, am I recording? Yes, I am. Okay, so let's start. Question 1. A curve is defined parametrically by x equals that and y equals 10, where t is between 0 to pi on 2. Show that the curve can be represented in a Cartesian form by this rule. Very, very easy. So you know how we have secant and tan? So secant and tan. Well, this you should remember. Look at your formula sheet, and you should look at this trigonometric identity. 1 plus tan squared t is equal to secant squared t. Now, I'm going to rearrange this in terms of tan and secant as the subject. So this will be x minus 1 is equal to secant t. And this is, y equals tan t. Now I'm going to stub them in here. So 1 plus, what's tan? You know how tan's y? Tan squared is y squared. Is equal to secant squared, which is just x minus 1 squared. Beautiful. So I'm going to expand both sides. So this, will be x squared minus 2x plus 1. And can you see how 1's on both sides? You can just cancel these ones out on both sides. There's really no need for them. And so, we get this. And, of course, we're solving for y. So y equals, of course, plus or negative the square root of this over here, x squared minus 2x. Now, which one is it? Is it the positive or the negative? Well, is y, your y value, is it positive or negative? Because remember, this, of course, is going to be, the whole expression here is going to be positive, especially it's a square root. But is it, positive or negative means that the y value, is it positive or negative? The way we check is to look at our thing, this here. You know how y equals tan t? Let's actually graph it. So if I graph this here nicely, tan, of course, it has a period of pi. So halfway, it will have an asymptote of pi on 2. So t pi on 2. I remember that's in terms of t here, and that's in terms of course, y, because y, yep. And drawing it, it should look like this. Like that. That's what the tan function looks. So what are the y values? Remember your y values, because y is in the y-axis. It's your range, basically. So because our range in this case is where y is an element from 0 to infinity, this tells me that y is positive. So hence, that's why y is equal to the square root of x squared minus 2x. Very, very nice question to start off the exam. Perfect. Next question. State the domain and range of the relation of this. Really, really easy. Like the way what we did. So when you have a parametric equation, what we're going to do is this. So we actually know the range because we, graph this and, we make sure we restrict it to this domain, of course, 0 to pi on 2. And we found that the y values that are acceptable are from 0 to infinity. So we already found the range, which is y from 0 to infinity. Okay, what about the domain? It's the same process. X secant t plus 1, you graph it too. So let's have a graph of that. Nicely here. Let's graph it. Okay, so imagine like secant, by the way, secant's 1 over cos, yeah? So imagine drawing a 1 over cos, like that, a whole period. And of course, when you're drawing it, the x values, because it's a secant, the x values here are going to be, of course, your asymptotes. So, of course, that's x, t equals, just be careful with that. So let me write, that's t and that's x. So that's, of course, t equals pi on 2. So imagine, let's rub this whole part out. We actually don't need most of the stuff out because we only want from 0 to pi on 2, remember? So that's an asymptote, and it looks, remember, the cosine looks like this, basically. Now, if you're going to draw the reciprocal, we know this is 0.1 here, and it will look like this. This is your secant graph. This is what it will look like. You have an asymptote at pi on 2 and 1. But don't forget you're adding 1 to it. Don't forget that plus 1. So imagine you're translating this this graph over here by 1 unit up. So it's around, let's just keep it in the same place, but it's going to be 2 here. So can you see how, what we're saying is, you remember the domain is what are the acceptable x values. You can see that this is our x, which is our range because it's in the y. So of course it's 2 to infinity. In terms of our, domain, it's 2 to infinity. Very nice. Perfect. That's really dark. Let me change the color. All right. Next question. Find dy dx in terms of sine t. Not too bad. So what we can do here is we know that dy dx is just dy dt times dt dx. Yes, isn't that right? Because these will cancel out and it just forms dy dx. Well, we have the expressions in terms of y, like, y equals, so we know y is equal to, of course, what was it? Tan t. So tan t, and x is equal to secant t plus 1. Just let me double check that. Yes, it is. So when you're deriving this in terms of t, it's going to be dy dt, which is, of course, deriving tan is secant squared t, and deriving x is dx dt is what? So, of course, deriving secant, you can do it basically, using the question rule by hand, but I'm going to do it with my cas. So let's go with my cas. I'm just going to derive in terms of t, secant t plus 1. Of course, plus 1 is just going to be 0 because it's a constant. So it's this. Let's write that down. So that's going to be equal to sine t all over cos squared t. So, of course, putting it in our expression, so, of course, dy dx. So what's my dy dt? We know dy dt is secant squared t, which is just, again, 1 over cos squared t. Cos squared t. Times by dt dx, which is the reciprocal of this expression, which is cos squared t, all being divided by sine t. And what happens is you can see that these causes will cancel out, and you're just left with 1 over sine, so 1 over sine t. That's in terms of sine t. Yes, perfect. Really nice question there. So it doesn't start off, it starts off really nice. Next question. State the limiting value of dy dx as t approaches pi on 2. Really easy. So we're just trying to basically find the limit as t approaches pi on 2 for our dy dx function. And our dy dx function is 1 over sine t. There it is, which is what? So use your calculator. So what we're going to do is we're going to go to limit. So limit is, where is my limit? Limit's here. And we're saying from t pi on 2 1 over sine t. 1 over sine t, which is 1. So that's equal to 1. That's your answer. Nice. Next question. Sketch the curve of this on the axis from 2 to 4, labeling the endpoints with the coordinates. Let's do that with our cas. So, and then we can just put it in here. So let's go to our cas and graph this. So the square root of x squared minus 2x from, which is 2 less or equal to x, less or equal to 4. And I'm going to make sure it's in the same scale as my, so this is what it looks like. So this, okay. So what is the y value? So that's 2 and that's 4. I just want to get those y values to be 100% sure. So f1 is basically this function, by the way, if you're wondering. It's my thing here. So what's f1 of 2? So yep, the y value, and f2 of 4. So, oh, sorry, f1 of 4. So okay, so the y value for 2 is 0, and the value for is 2 root 2. So let's do that. So for 2 here, it's going to be the y value for this 2 here is going to be 0. And for 4, it's going to be 2 root 2, which is basically control enter. It's 2.8. So 2.8, which is 2.5. So 2.8 is around here. Somewhere around here. Perfect. And it's going to look like this. The graph look like that. Perfect. Something like this. Nice and smooth. There it is. Okay, why is it so ugly there? Something like that. Done. And of course, what did the question tell us? Label the endpoint. So you remember, okay, this endpoint here is 2, 0, and this endpoint here is for 2 root 2. Done. Really, really nice question there. Next question. The portion of the curve is given by this from 2 to 4 is rotated about the y-axis to form a solid revolution. So what's happening is, imagine this here gets rotated around the y-axis. It will look like this. So you'll have this over here. Of course, the 4 part would be over here. And so imagine this over here. And it just gets rotated around the y-axis. You form this solid over here, this solid shape. All right. So let me just take that out. That's what it should look like. Write down, but do not evaluate, a definite integral in terms of t that gives the volume of the solid formed. So we know to find the volume, it's pi integral. Well, in terms, okay, so we're on integral. What is the, because we're rotating in the y-axis, it's going to be dy, and these values are going to be in terms of y. Well, we're rotating it from, in terms of y, is 0 to 2 root 2. So 0 to 2 root 2. And remember, because you're rotating around the y, you have to have x squared in the middle. What's x squared? That's really easy, and we want it in terms of t. X squared, going back to our original question, is x is equal to secant t plus 1. Imagine squaring it. It's just this whole expression squared. So this whole expression here, or squared. So it's secant t plus 1. Let's go down here. It's secant t plus 1 or squared. Write that nicely. Yep, secant t plus 1. Now, there's a big problem. You remember how we said these are in terms of y? We need to convert them in terms of t, because remember, we are having it the expression has to be in terms of t. Well, because these are in terms of y, let's go to our y equation. Y equals tan t. So let's write this down. Y equals tan t. If I know this is y equals 0, what is it convert? Like, what does it convert in terms of t? So if I sub in, this into the y and solve for t, of course, t equals 0. If you solve that, it's just the same, basically. It's 0. But what about, how this isn't y? So let's put that also, and let's find what is it in terms of t. T equals tan t. It's just going to be the inverse. So the inverse of 2 root 2, that's going to be your t. So we can replace that with that. So tan 2 root 2. Done. So, okay, and there's one more thing that we are missing that's in terms of y. It's our dy. So, can you see that dy over here? Well, okay, you remember how we said y equals tan t. If I derive that, don't we get dy dt equals secant squared t? And if I multiply by both sides by dt, I get rid of this dt over here. So now I got an expression in terms of dy. So I can actually substitute this expression for the dy. And now it's in terms of t, as you can see. So secant squared t dt. All right, let me rub that out. And there it is. Really, generally, wow, it's a lot of work for 2 marks, but that's how you would approach this question here. Okay, perfect. Question 2. So we've tried this. Show that the solutions of this, where z is a complex number, are this. So it's just a normal quadratic. Let's use the quadratic formula. So the quadratic formula, of course, is so z is equal to negative b plus or negative b squared minus 4ac over 2a. Now, you don't need to write it, but I'm just going to show it. Yep. So z equals, what's our b? Well, it's negative 4. Plus or negative, so b is of course 4, but it's going to be negative 4 because of the b. Yep, b squared is 16 minus 4, a is 2, and c is 5, all over 2a, which is 4. 2 times 2, which is 4, yep. So let's simplify this. So this here, this expression over here, so 5 times 10, that'll be 40. That'll be 40. So 16 minus 40 is negative 24. Okay, I'm going to take that negative out and put an I. Because that simplifies to I, of course. I outside. Let me just make, this is too long, actually. Like that. Okay, I. We can simplify this, 24, because you know how it's, isn't it, so, 6 times 4, 6, 12, 18, 24. Yep, 6 times 12. So we can write that, root 24 as 2, which is 4 times 6. 2 root 6, basically. See? 2 root 6. 2 root 6i. And what we can do here is you can see that we can actually simplify it because we have a common factor of 2 on top and bottom. So it's just going to be z is equal to negative 2 plus or negative root 6i all over 2. We're making good progress. Now, of course, just separate them. So z hence equals negative 2 divided by 2 is negative 1, plus or negative root 6 all over 2i. Perfect. And we've shown that's the solutions for that one. Beautiful. Next question. Plot the solutions of this on the Argand diagram. Easy. So, one of the solutions, negative 1 plus root 6 on 2. I don't know what root 6 on 2 is in decimal, so let's write that in our calculator. Root 6 on 2 is 1.2. So 1.2. So negative 1, positive 1.2, which is around here. Right there. Negative 1 to 1.2. Perfect. Around there. And of course, negative 1 over root 2, which is just over here. Yep, because they're going to be negative 1.2. So these are your two values over here. So I'm going to just label those. So in terms of coordinate, that's going to be negative 1, comma, negative root 6 on 2. And this one here is negative 1 plus root 6 on 2. Easy. Perfect. Yep. 1 mark. So next question. Let the absolute value of z plus m equal n, where m and n are real numbers, represent a circle of a minimum radius that passes through the solutions of this. Find m and n. Now this is a normal way you would write. Like this is the equation of a circle. Remember, an equation circle is normally written like this here, the way they've written it. So it's like minus a minus bi, absolute value equals r, where this value over here is your radius. If it's written, yep, this is your radius. And this here, when you solve it for z, let this equal to 0 at the, is going to be equal to a plus bi, which is, in terms of coordinate, ab. And this is your center. So it's center of that circle. So, okay, we've kind of understood what's happening here. So imagine, using this knowledge here, what it means is that this m over here, of course, is your radius of that circle. And m here, because m is a real number, it has it's not a complex number. It's just, it's a real number. Means that in terms of coordinates, when you solve this, what we said, z equals negative m. And so because it's a real number, there's no complex. It's basically negative m 0. This is your center because there's no imaginary part. So it's like negative m plus 0i. There's no imaginary part. So there it is. So this is your coordinate of the center for this equation. All right. So these are your center for this equation. So that would be the coordinate of the center. Okay, we want to represent a circle of minimum radius. Minimum radius means the smallest radius that we can produce. We want the smallest radius that passes through those two solutions. And we want to find those values of m and n. So let's think of cases. Okay, well, we can have a case where if I draw a circle that passes through these two, like that. So it's passing through m and n. Look, it has a radius, normal radius. Okay, but is that the smallest radius? Because remember, we want the minimum radius. Like if I move it more to the right, like if I move it a little bit further to the right, what's going to happen? I have to make it bigger. Can you see? Move it more to the right, I have to make it bigger. This is a problem. So moving it to the right is not going to be a great way because it's making it bigger. What about moving it to the left? Yep, you can make it smaller. A little bit, move it more. Make it more smaller, that it passes through those points. This is great. Move it more. It looks like, passing it. And until you hit this position over here where you get actually that it passes through all those points where it passes like this. This is the best time where the radius is the smallest. Because if we move more on the left after that, guess what's going to happen? It has to become bigger again. So the smallest radius is when the circle is actually, these points over here are lying like this. This is where the smallest circle is, where the minimum radius is. So perfect. This is what it is. So what is the center point? Well, we know that the center point is on this point here, negative 1, 0. So which is these coordinates over here, negative 1. So it's negative 1, 0. And it generally makes sense because, like what we said, we know that the m value, that it's not it has to have the y value 0. So can you see how that's also 0? Negative 1, 0. Perfect. So our radius, our center point is negative 1, 0, which hence our m, remember our m has to be 1. So m value equals 1. Okay, what about our n value, which is our radius? Well, let's have a look here. What is our radius if it's over here? Well, it's easy because, this is 0. Well, isn't this the radius? Well, the y value is root 6 on 2. That's your radius. Root 6 on 2. So, because 0 plus root 6 on 2. Yeah. What happened there? Yeah, root 6 on 2. So your n value here is root 6 on 2. Done. There it is. All right, perfect. Next question here. Find the Cartesian equation of the circle of this. This is easy, really easy. Just the Cartesian equation, just the normal way you would write a circle. Well, if we know the center of it is, again, what was it? So it was -1, 0, and the radius was that root 6 on 2. Well, you would write a circle like this then. It will, because there's, an x value, so you would write it as x plus 1 squared, so the center is -1, plus the center for the y is going to be y squared equals radius squared, which is the radius, of course, is root 6 on 2, and you square that, it's going to be 6/4, which is 3 on 2. This is the form that you would write the center that represent this circle, because this here, you solve it to equal 0, it's going to be -1. This one is going to be 0. That's your center, and then, of course, take the square root of 3 on 2, which gives you the radius. So not too bad. Really good questions here. All right. Going down. Sketch the circle on the Argand diagram in pi-intercepts with coordinate axes do not need to be labeled. Okay, this is perfect. So yeah, just basically this over here, the way we did it here. We don't have to label any, intercepts with the, that looks perfect. Done. Next question. Find all values of d where d is an element of a real number for which the solutions to this satisfy this equation. Okay, so this equation here is the equation that we got, of course. So you know how it was z plus m, and what was our m value again? M plus 1 was 1, and less or equal to n. What is our n value? Our n value is root 6 on 2. So we wanted to satisfy this part over here. Now, if it satisfies, it means that this, so the solutions of this, let's find the solutions. So the solutions to this, of course, is using the quadratic formula, which is, of course, negative b, which is -4, plus or negative b squared, which is 16 minus 4, a is 2, and c is d, all over 2a, which is 4, which is equal to -4 plus or negative square root 16 minus 8d, all over 4. And you can see that there's a common factor that you can take out over here. You can write this inside here as, take a common factor of 4. So 4 minus 2d. You can write it like that, this part inside here. So, and then of course, you take the square root of 4, that 4 outside is going to be basically 2 square root 4 minus 2d. And then you can simplify this further on, because now there's a common factor of 2. You can make this a 2 here, and make this a 2 here. So this is our, it's getting simplified. And of course, overall, this is our solution. So our solutions are overall z is equal to, what's -2 divided by 2? It's -1 plus or negative the square root of 4 minus 2d all over 2. So can you see how I just simplified it? Yep, made it as, okay. So imagine if this satisfies, if these solutions are to satisfy this equation, it means that if I sub them in here, I have to solve for d. So like if they satisfy, it means that when I fit them in here, this whole equation, this whole expression is true. So what I'm going to do is I'm going to sub, well, there's two cases. Of course, there's the positive and negative. So I want to make sure that there's two cases. So I'm going to write this positive one first, and I'm going to just, and there's, of course, the negative one here. So I'm going to write that here, and, of course, the negative part here. And I'm going to put them over here. So I'm going to sub in the first one into this expression. So when z is -1 plus square root of 4 minus 2d over 2 plus 1 is less or, let me make this longer. Yep, is less or equal to root 6 on 2. Guess what? You know that -1 and +1, they cancel out. You can see how they cancel out. And so the absolute value of this, we can just use our calculator to calculate this, by the way. So what's that in terms of, calculate the value of d. So let's use our, calculator here. No, before we do that, actually, let's just do that also for the other case where we have, well, let's do it for the other case too. So the same expression. So, of course, so z is -1 minus the square root of 4 minus 2d, all being divided by 2, plus 1. Again, this cancel out. These ones will cancel out again. So there's oopsie. So these ones here will cancel out. And you're basically left out with this over here. Absolute value root 6 on 2. Now, to be honest, I think they're the same equation because you're taking the absolute value of this negative. It's just going to cancel. I just want to make sure. I don't want to make any mistakes. So let's put these, one of them each, and let's see what solutions of values of d we should get. So let's use our cas. So the first one is what? So the absolute value of the square root of 4 minus 2d divided by 2 is less or equal to root 6 on 2. Root 6 on 2, comma d. Oh no, sorry, big problem. That's not supposed to be there. That's supposed to be outside. There it is, and of course, which is that, and then of course we solve. Just put this expression here, comma d. So our d value is between -1 to 5. What about the other one that we did when we had a negative here? So the same thing. Yeah, they're the same thing. So these are your d values. So let's write that down. So your d value is between -1 to 5. Beautiful. There it is. Next question. All complex solutions of this have all complex solutions of this expression have a non-zero real and imaginary part. So they have, of course, a real part and an imaginary part. Perfect. Let the absolute value of z plus p, basically like an equation of the circle, represent a circle of minimum radius in a complex lane that passes through these solutions where, it's basically like the same context as the other one. Find p and q in terms of a, b, and c. So we're basically trying to find this, like m and n, but it's like the whole same thing. This is not too bad. So what I'm going to first do is, if you thought about it, if it passes through this solution and we want the minimum, it's like the same case as these ones over here. Can you see how, we find the solutions, and the x value is going to be the same for both, of course, and that's going to be and of course, take the negative out of it. You know how m was equal to 1? Yeah, that's what we're going to do. So let's actually find the solutions first. So, of course, it's a normal quadratic, because it's in terms of a, b, and c, so we're just using the negative b plus or negative b squared minus 4ac over 2a. Okay, so these are, and of course, split them up, which is equal to negative b over 2a plus or negative, b squared, so it's square root b squared minus 4ac over 2a. Okay, so remember, this is our coordinate. This is our x coordinate, which is like in that case is -1. Of course, we take the we take the positive part of it, not negative, but the positive. You remember, our m value was 1. The same thing in that case. So this value here is our p value, which is b over 2a. You remember, you take that negative out. There it is. Now, I just want to make sure, does this make sense? So p is a real number. Okay, it's a real number. And yep, this is real number because b and a are real numbers. That works perfectly. Is there anything that's going to... Yeah, so p is a real number. And yep, so p represents a token that passes through the solutions where it has a real number. Okay, real number. Okay, perfect. So yep, that looks good. That looks good. That one looks good. Okay, what about the other one? So what about your q, which is our radius? Well, you're coming back here. Well, so it's going to look like this, but basically, how this is the y value was our radius, of course, but there's, you have the plus or the negative. We don't know what it is, but we know for sure if we take the absolute value, it's going to give us always the positive, because remember, the radius has to be positive. So kind of think of it like this. Can you see how, we got, imagine that, are these two, the plus or negative. And of course, if we take the absolute value, we always make sure we get the radius for both. And remember, especially in this case, because you remember, we don't know what b and a, because a can be negative and c, so it's going to mix us around. That's why we want to use the absolute value signs. So basically, your q would be the absolute value, this whole absolute value expression of this, the square root of b squared minus 4ac over 2a. Now, don't forget one thing that's important in this case. It said that that there's an imaginary part. This here has to be imaginary, yeah? Because it says non-real and imaginary part. So the solutions, of course, this is the real part, and this is, of course, there has to be an imaginary part. For it to be the imaginary part, this here, this inside here has, you know, the discriminator must be less than 0 for it to be a complex number. So to be imaginary. So what it has to be is that b squared minus 4ac must be less than 0. It has to be a negative number. We'll consider that right now. So let's just let's see what this simplifies to, that q1. So putting in our cas, absolute value square root b squared minus 4 times a times c over 2a. And it simplifies to this. So let's write that down. So set that down. So absolute value of this whole expression, so like that, which is 4ac minus b squared absolute value to absolute value a. Okay, so we've kind of simplified it to that. So I can rub this part out and come back to this one here. I don't want this here. All right, so this is what our q value is. Now, like we said, we need to make sure that this part over here is, you know, imaginary because of this. You remember this here expression? You remember how we wanted this to be imaginary? We must have that discriminant to be less than 0. This is where the problem is. Now look at it. If I know the bottom part, you remember we want q to be basically imaginary, but we're saying. So if 2, like, you know, not imaginary, like what we're saying is this part here to be imaginary, the top part. So overall, you know how this part is real, because remember 2 is, you know, it's a number, and if you're taking the absolute value of a, it's a real number. The bottom's real. That's okay, that's good. So, but this part over here is also real, because remember what we said, if 4 minus ab here, it could be real or imaginary, but if you're taking the absolute value of it, you're gonna make sure it's real. That's a problem. So this whole q value, no, this whole expression over here is actually becomes real. So we don't actually meet the requirement for imaginary part. How do we fix that up? We take those imaginary parts out, these absolute value now. Because now in this case, it could be imaginary or real, but of course imaginary in this case. So this is how we can fix it up. So done. I hope that makes sense, and we've kind of met all the requirements for this question. So there it is. I'm generally, to be honest with you, this is a really hard question, I remember. So I hope that makes kind of sense. All right, so yeah. Next question, 3. Let's have a try at this question over here. It says, the graph and decay of quantity p with respect of time is modeled by this differential equation. So p is like a population or something, where t is greater or equal to 0. Given that p of a equals r and p of b equals s, where p is a function of t, show that k equals that. Okay, not too bad. So let's do it. So what I'm going to first do is I'm going to, you know, reciprocate this, because I want to get it as, of course, dt over dp, which is 1 over kp. And I'm going to, you know, take the integral. So I can take that 1k constant out. I'm finding the integral of 1 over p in terms of dp. So that's going to be, of course, you know, the absolute value of p. But remember, p is like quantity, like a population. So it's just going to write as p. I don't think, yeah, p plus c. And yeah, we have the c as a constant, so we can actually just sub one of these to kind of get c. Let's sub in a, this one here, the first one. So when t equals a, your population is r plus c. So we can actually solve for c, which is basically a minus 1 over k log e r equals c. And I can sub that to the original equation, which is, you know, t equals 1 over k log e p plus a minus 1 over k log r. All right. So we can a little bit simplify this much further, like, because you know how you got 1 over k log p and minus 1 over k log r, that becomes 1 over k. So let me do a bit right in nice. 1 over k log, you know, p over r plus a. And now we want to sub in this p of b of s, because we want to look, there's no you know, p and s, so you know, p and t in terms of p and t, so we're going to sub b and s. So when t equals pb, so that your p value is s, then s over r plus a. And we're going to need to, I'm going to minus a on both sides, so it's going to be b minus a. And I'm solving for k now. Log e of s over r. So I can kind of reciprocate this, so that becomes a k here, and that's going to be 1 over b minus a log e S over R. But it's supposed to want A minus B. So what I'm going to do then is I'm going to take, rewrite this nicely. I'm going to take a negative, like, I'm going to take a negative out this whole expression, which is now 1 over A minus B log S over R. You remember what happens in log laws? If you have a negative, you can actually bring it inside the log. So if you bring it inside the log, it'll look like this now. S over R to the negative 1, which is basically the reciprocal, which is just R over S. And so, yes, we got our final answer, which is what we wanted. So, all right, A minus B log E R over S. Done. Not too bad. Okay, so that's there. Next question. Specify the conditions for which K is greater than 0. So when K is positive. So let's write what this formula is. Yeah. So let's, you know how it's K is equal to 1 over A minus B log E. So log E R over S. So we want this expression K to be positive. So because there's two products that are being multiplied, what are the cases that we can make sure we can guarantee that this whole expression is positive? There's two cases that these two expressions here are both positive or both negative, because negative times negative is positive, or positive times something with positive is always positive. So we have two things that we need to look for. So let's look at the first case, of course. So the positive. So what has to happen is that 1 over A minus B, this expression here, so this expression here, has to be greater than 0 to make sure it's positive. And of course, also the case where log also has to also be positive. So this is your first case. Okay, now let's think about it. Here, 1 is positive. Remember, we want this whole expression to be positive, greater than 0. If 1 is positive, yeah, we want overall to get this positive. We need to make sure the bottom is also positive. So we also want the A minus B to be greater than 0. So A is greater than B. Done. That's the first part. So now we can guarantee that this is also positive, because positive divided by positive is, of course, positive. So greater than 0. So we've kind of specified that that when A is greater than B, that's the first one. And what about this one here too? All right. So, e to the, so make sure like, basically e to the power of both on sides. So what's e, this becomes, this simplifies to R over S, of course. And e to the power of 0 is 1. That simplifies to that. And of course, multiply both sides by S, we get R is greater than S. That's your other condition that needs to also be specified. So your two values, and that. So these are your first two cases. You can get this one over here, of course, or remember what we said, the negative part here. So we want basically the 1 over, so we want 1 over A minus B to be less than 0, so it'd be negative, and also that log part to also be negative, so less than 0. Okay, so if this is positive, yeah, and we want this whole expression to be negative, don't we have to make sure the bottom part's negative? So we want the A minus B part to be less than 0, so A must be less than B. So that is the first part here, A must be less than B for this part here. And what about this part here? Let's also do this. So again, the same case like what we did, e to the power, but like this will become R over S less than 1, so R must be less than 1, so times both sides by S. R must be less than S, yeah. R must be less than S. That's your other condition. Those are the two conditions. Done. Perfect. Hope that makes sense, and we are done. That's that question. So these are the two, these are conditions, these are the specific conditions for which K will become greater than 0. Let's look at the next question. The growth of another quantity Q with respect of T is multiplied is differential equation where T is greater or equal to 0 and Q equals 1 and T equals 0. Basically, this is an initial condition they've given us here. Let's look at the question. Express the differential equation in the form of this. This is easy because remember, this is just a separation of variables because you got in terms of T and Q. So think of it like this. We can write this expression dq over dt as et times e negative q, because remember using your exponential laws. And think of it what we would normally do. We would, to get, how that's in terms of q, we would do integrate 1 over the reciprocal of it, so e power of negative q dq is equal to the integral of et, so et dt. And so you know how that's just the that simplifies basically eq dq is equal to the integral of et dt. And can you see how these are functions? Like you got the fq in terms of q, the function, and we got ht in terms of t. Done. This is how you would kind of simplify that. That's really typical. That's really easy, this one. This was a really nice one. So, yeah. So let me just move that like that. Okay, next question. Hence, so using this here, show that q equals that. Okay, so let's do that. So we know, of course, so we need to integrate eq, which is just basically, again, eq by itself. And integrate this in terms of t is just et. And don't forget that plus c. So we need, of course, an initial condition, which we are given already, which is that when q equals 1, t equals 0. So it'll be e equals, plus e to the power 0 is 1 plus c. So your c value is e minus 1. So subbing that into the function, eq is equal to et plus e minus 1. And so solving, of course, it's going to become q. The q part, because we're solving for q, is just going to be the log of et plus e minus 1, which is the equation that we are given above. So beautiful. There it is. Okay. Next question. Show that the graph of q as a function of t, so what we've got here, does not have a point of inflection. So we know for something to have a point of inflection, the double derivative must equal 0 if there's solutions. Now, what I'm going to do is let's find the double derivative. So so of course we want to find the double derivative. So I'm going to derive it first, like dq dt, which is in a log, it's really easy. Remember logs, when you derive logs, so ddx of any log. Let's say you have a log and a function, it's like log e of a function, so like that. The derivative of it is, remember, it's just the f dash of x over f of x. So this is what I'm going to do. So I'm going to basically derive the inside, which is basically just et, because remember these are constants, and then rewrite it, the bottom part here. So this is the first derivative, and then I'm going to find the double derivative. So derive it again. So yep, dt squared is equal to, and now we're going to, of course, because two things are divided, we're going to be using the quotient rule, where this is u and this is v. So you remember it's going to be v plus e minus 1. Times u dash, which is just the same thing, so et, minus u, which is et, times v dash, which is basically, these are constants, so it's just et, times et, all over v squared. So et plus e minus 1 all squared. Okay, so this is equal to 0. Like, is it gonna give us any solution? So let's just simplify. We can just do this. Let's actually simplify it first, because I think, yeah, it's going to be simple. Let's expand this top part out. So it'll be e 2t, because, times that, plus e t plus 1, minus et, minus e 2t, et plus e minus 1 squared. So you can see that these cancel out. This part here cancels out with that part. And we get this here, this whole nice easy expression. Now, okay, so does this equal 0? I have no idea. So let's use our cas and let's see if there's any solutions to this part here. So it says, t plus 1 minus e, minus et, et plus the constant e minus 1 squared. And that gives me, like, of course, equals 0. Solve answer, comma t. False. So there's actually no solutions. So why? Well, kind of makes sense. Like, I know that the fact that the bottom part here is positive. We know it's a greater than 0 because, of course, it's some value and then you're just squaring it. So it's always going to be positive. So we know that the bottom part, so let's write this bottom part here. This, et plus e minus 1 is going to be greater than 0. It's a positive thing. And, no, actually, before we do that, let's actually graph it too. Let's go back to our cas. Let's also graph it, because if I can graph it, I can see if it's actually greater than 0. No. So that's in terms of, I want to get it in terms of x, of course. In terms of x. There it is. Can you see how it's greater than 0? Because there's an asymptote at y equals 0. So it's always, the whole function is greater than 0. So coming back, So, yep, this is greater than 0. And what about this part here? Is it greater than 0? Well, we can kind of double check it. Is et plus 1 minus et greater than 0? So bringing that this part here to this side, which is going to be et. And can you see how there's e on both sides? So they just cancel out. So it's going to be d plus 1 is greater than t. T is basically also cancel out. Because you minus them. Is 1 greater than 0? Yes, it is. So this whole statement works. So it is actually true that even this part over here, that et plus 1 minus et must also be greater than 0. So if both parts are greater than 0, then whole your overall dy dx is greater than 0. It doesn't even cross the x-axis where there is a point of inflection. So we can state that hence your d squared q dt squared is greater than 0. It doesn't even equate to 0. You can also do this by this way. Like, if you're not sure, what we can also do with our cas is to take this here and be like, is this greater than 0? Oh, it doesn't really kind of do. I thought it was going to do it, but don't worry about it. Yeah. That's basically it. So done. That's so there is actually, it doesn't even cross the x-axis, hence there should have been any solutions. Done. What about question 4? The base of a pyramid is a parallelogram ABCD with vertices of this A, B, C, and D. The apex top of the pyramid is located at P. Find the values of A, B, and C. So, okay, let's kind of draw a diagram here because I truly cannot understand what's happening here. So I'm going to just draw a nice parallelogram here. Remember what are the features of a parallelogram? Can't even say that properly. Here, let me draw that nicely. It does the job. It does the job like that. Okay, so this is a parallelogram. What's cool features about a parallelogram is that these two sides are actually equal in length, and also these two sides are equal in length. The thing about that, because it's called a parallelogram, it's parallel. So these two parts here are parallel, and these two parts here are also parallel. So these two sides are parallel. If you kind of think about it, if the magnitude and the direction are parallel, this vector here is the same as this vector. And this vector here is the same as this vector, basically. Just kind of, what did I do there? What did I do? Let me move this out. I was supposed to put it here. Yeah, there it is. Okay. So remember there's an apex on top. So let's say this here is the top part here. So they're all go on it. It's like a pyramid. So that there, this there, this part there, and this part there. Okay, so this is your P, and this was, because this is A, let's say this is B, and this is C, and this is D. And this is what it looks like. This is what the pyramid looks like. We want to find the values of A and B and C, so the coordinates of C. Now, that's kind of easy, because remember what we said. You know how AB, this vector AB. So you know how vector AB, this vector AB, isn't it going to be equal to the vector DC? Because you remember what we said? If they have the same magnitude and the same direction, aren't these just the same vectors? Yep, they are. So AB is actually just equal to DC. So what we can do is, find those and equate them. So what I'm going to do is AB, to find, of course, AB, it's really easy. So we know AB is just your, it's just negative OA plus OB. How do I know that? Well, it's easy. Remember, when you're trying to find AB and you want to write it in terms of O, the first expression, just write it as negative OA, always negative, and this one plus. So for example, I want to find DC also. So DC, because you know how D is in front, I'm going to write it as negative OD plus OC. That's just a quick trick. So I'm going to define all these vectors on my calculator and find AB and DC really easily. So let's do that. So I'm going to go to my CAS and I'm going to control N everything here, so I don't do too much messiness. So my vector A, so OA basically is this vector, which is looking at it's 2, -1, 3. B vector, yep, so 2 is that's -1, that's 3. The B vector here is 4, -2, 1, 4, -2, 1, yep. Your C vector is your A, B, and C. Oh no, okay. There's kind of a really big problem here because we don't know. Let's call it A1, B1, C1. Because you know how we know we're A, B, and C, but we're using A, B in here, so we don't want to mix it around. So I'm going to call A1, B1, and C1. And I'm going to enter, so that's also defined. My D vector is what? So my D vector is 4, 3, -1. And my P vector, P, so your apex, is 4, negative 4, 9. There it is. So we got all these vectors defined, and I was trying to find AB, which is, of course, AB is just negative A. So that's negative OA plus B. This here is my AB. Let's also find DC, which is negative D plus C. Take that out. Enter. So this is my vector, of course. Remember what we said. This is my vector AB, and this is DC. So let's write those down. So I can kind of rub this out. I don't need these out anymore. So AB is basically 2I minus j minus 2k. Yep, 2I minus j minus 2k. And the other one here is a minus 4i plus b minus 3j plus c plus 1k. Now remember we said AB and DC are equal, so we can equate the I, J, and K components. So let's do that. So this here equates to 2. So A minus 4 equals 2, comma. B minus 3 equates to negative 1. And then, C plus 1 equals to negative 2. Hence, these are going to be, what? A equals 6, basically. B equals 2, is that right? Because negative 1 plus 3. Yep, 2. And C equals negative 3. Yeah, negative 2 minus 1. Yep, negative 3. So these are my values. Done. Okay, these are my A, B, and C values. Done. Let's go to the next question. Find the cosine of the angle between the vectors AB and AD. Okay, so if we're finding the cosine, you're basically like finding close to this angle here. So it's the angle AB. So AB is that and AD is that. We're finding this angle over here, basically. Like the cosine of this angle, actually. So, of course, it's really easy. Isn't it just AB dot AD equals the absolute value of AB times, times AD, the magnitude of AD times cosine theta. That's what it is. So, I'm not going to lie, this is really, really easy because it's 2 marks. Okay, so we got AB. You remember AB is right over here. So let's find the so I'm gonna write this. So what's AB? So AB is 2I minus j minus 2k. So yep, there it is. So 2I minus j minus 2k dot, so times AD. So what's AD? Let's find it in our cast. Remember, AD is just negative A plus D. So AD is negative A plus D. Enter. This is AD. So let's write that down. Times, so 2I plus 4j minus 4k. Minus 4k. Is equal to, of course, the absolute value of those values. Now, it's really easy to find those because we can just use our calculator. Like the absolute value is just called norm. So we can say norm. Norm means the absolute value of the first one, which is negative A plus B, which is this here, is 3. And let's also find the magnitude of, we also need to find the magnitude of AD, which we just found out, which is negative A plus D, which is this here. And yep, 3 and 6. So let's write everything down. It's basically 3 times 6 times cosine theta. So, of course, this is really easy. The dot product of these, just 2 times 2, which is 4. Negative 1 times 4 is negative 4, and negative 2 times, negative 2 times negative 4 is positive 8. So it's basically just 8 here. So 8 equals, so 6 times 6, 12, 18, 18 equals cosine theta, 6, 12, 18, yep. So 8 over 18 equals cosine theta. I just want to make sure, have I made any mistake here? 2 times 4. That looks good. So yep. So that 8, that divided by 18. How many 2's go into? So they're divided by like cosine theta. I don't know what just happened to me. Divide that 8 by 2 is just 4, and divide 18 by 2 is 9. That's your answer. Done. All right. So that's your answer for that one. Not too bad. Not too bad. Okay. Okay. That's the cosine of the angle. Next question, find the area of the base of the pyramid. Easy. Now be careful. This pyramid, like the base of the pyramid is not right, and these are not right angle to, there's some angle. Remember, there's some angle. So it's not that easy. It's not like, it's like a rectangle and you just multiply the area. So we need to be careful here. So what I'm going to do is we split these two into a triangle, because we know that this here, area of this triangle, it has to be equal to this area. So they're not like you just find the area of one triangle and double it. So if you kind of think about it, look at this, because it said, yeah. So what I'm going to do is this. Let's try to find the area of this triangle and then, of course, double it. Now, to find the area of a triangle, it's basically, of course, area of a triangle. This is not a right angle triangle, by the way. It's the half BC times sine A, the area A. It's in your formula sheet. Okay, so of course what it is let's say okay, we actually know this angle here, by the way. We know this angle because we know the cosine 4/9. So let's call this, ends at A. So basically let's call this the angle A. Yeah, this is called the angle A, and this has to be, of course, this has the angle B. So this has to be B and this has to be C. So this part here has to be B and this has to be C, and we can find this area of a triangle using that. So basically, kind of simplifying it, what we're saying is this. Half B is, remember what B is, the magnitude of AD, basically, which we know what it is. So magnitude of AD times C, which is basically AB, so the magnitude of AB times sine A. A, remember how this angle was theta? We considered it as, so you consider it as just theta. Because remember cos theta here? Okay. We consider it as theta, just to make it more sense. Yeah. All right. So we can actually come down here and a little bit simplify some stuff here. So, okay. So we know that the absolute value of AD was what? It was 6, I think. Yeah. So it was, it was, so, 6. So 6. And the absolute value of AB, which was 3, times sine theta. Okay. Now I'm going to use a right angle here. Right angle triangle, because we have cos theta, but we don't have sine, so we're going to use a right angle triangle here. So imagine this is your theta angle. So you know how cos is adjacent over hypotenuse. So basically, that's 4 here, and that's 9, and of course we're going to try to find this over here. And so that's just using Pythagoras theorem. So what's 9 squared, which is 81, and what's 4 squared minus 16? That's going to be the square root of okay, so 60. So if I put 64, 65, because that plus 1, yeah. Does that make sense? So if I put 64, 7, 8, yep, 65, root 65. That's going to be root 65 here. And so, remember what is sine? We know that sine is, of course, opposite over hypotenuse. So this part would be, the opposite is that root 65, and our hypotenuse is that 9. So a little bit simplify this much further. Let's think about it. So, think about it. Half times 6 is 3, so this becomes a 3. 3 times 3 is 9. That becomes a 9. 9 times, these 9s will cancel out. It's basically equal to root 65. Root 65. Now be careful. This is not your area. Remember, this is the area of one of these triangles over here. So we have to double it to also that one. So it's the overall area is this here, but doubled. So 2 root 65. Hope that makes sense. There it is. Units squared. Okay. Okay. Done. Have I made any mistake? Looks good. Next question. Show that this vector is perpendicular to both AB and AD, and hence find a unit vector that's perpendicular to the base of the pyramid. Okay, wait. Let's think about it. So show that this vector first is perpendicular to both AB and AD. So to show something that's perpendicular, the dot product must equal to 0. So if you multiply this, if you find the dot product between, let's consider this vector here to make it easier. Let's consider this vector here. Let's consider this vector as n, vector n. So basically, we need to do 2 dot products. We need to find the dot product between this and n, and of course it has to equal to 0 if they are perpendicular, and the same case for A and D. That's going to give you the first 2 marks, and then we'll do the other part, which is, find the unit vector. So let's do the easy part first. So n times AB is what? So n is what? N is, 6i plus 2j plus 5k times AB. So, so AB, I'm looking at my CAS, what was, which is, so AB, which is negative a plus b, is just 2i minus j minus 2k. Okay, so kind of this simplifies to what? So 6 times 2 is 12. 2 times, negative 1 is negative 2. 5 times negative 2 is negative 10. And what does that equal? That equals 0, sorry. That equals 0, which is great. If your dot product equals 0, then hence, it is, they are perpendicular. So, done. So, hence, so basically, n is perpendicular to the vector AB. Done. Also, the same case for the other one, dot AD. So let's write that down. So 6i plus 2j plus 5k dot AD is negative a plus d, which is look at my cast, and 2 plus 4j minus 4k. Okay, so that's going to be 6 times 2, which is 12. 2 times 4 is 8. 5 times negative 4 is negative 20. And that equals 0. Perfect. So also the dot product of this, so the vector n is perpendicular to also AD. Done. Okay, that's easy. And then it says, hence, find a unit vector that is perpendicular. So it has a unit of 1 that is perpendicular to the base of pyramid. Okay. So this n, yeah? This n vector. Because it's perpendicular to AB and AD. Let's come here. To this here. Let's rub this part here. So, let's rub some stuff out like that. Okay. So, because it's perpendicular to AD, yeah? It could be, like, AB is here, yeah? It could look like this. Can you see how that's perpendicular? It could look like this. This could be the n vector. Can you see how it's perpendicular to AB? And, yep, so that's one, it could look like that, basically. And also it's also perpendicular to also, like, if we take it, this vector also, because it's also perpendicular to AD. Yep, can you see how AD is here? This vector here. AD, they are perpendicular also. That's also perpendicular. So guess what? Your n vector, this part here, is actually perpendicular. Can you see how it's perpendicular? But isn't it also perpendicular if you bring it? Isn't it perpendicular, like, to the base? Can you see how this is your base of your thing? And can you see how it's like perpendicular to the base of the pyramid? The base of the pyramid, yep. And hence find a unit vector that is perpendicular to the base of a pyramid. It is actually perpendicular to the base of a pyramid, as you can see. So this is actually great. This calls for great calls because okay, we got that. That's actually perpendicular. This is really, really good. So, but remember, this is a directional vector. We want a unit vector, which is quite easy to get. Remember, a unit vector. So we know a unit vector is, so for, like, we want the unit vector for this, basically. The unit vector, which is just 1 over, n, the absolute value of n, so the magnitude of n times n itself, which is, what? So 1 over, what's the absolute value of n? N is this, so it's just, 6 squared is 36, 2 squared is 4, 5 squared is 25. So it's basically, that's going to be 40 plus 25, root 65. Okay, root 65, so root 65 and vector n. So n again, just that 6i plus 2j plus 5k. Done. There it is. That's it. Because that's the unit vector. So basically, but remember, that's the unit vector, yeah. So when this has 1 unit, the magnitude of 1. Done. Yeah, that looks good. Find the volume of the pyramid. So we want to find the volume. So looking at your formula sheet, what's the volume? How do you find the volume of a pyramid? Well, finding a volume of a pyramid, so volume is equal to, let me look at the formula sheet, it's 1/3 area times height. Area is the area of the base. And we know what the area of the base is, so this is quite easy. The area of the base is, we just got it from the other question, 2 root 65. So 2 root 65, but of course, height. We need the height of that pyramid. So we want the height of this from P, we want from P to this over here. How do we get that? Well, let's think about it. Okay, so you know how we have this directional vector, yeah? You know this n, yeah? Isn't it the direction? Can you see how it's a directional vector to the base of the peak? But be careful. The problem with it is that we know it gives the direction. It's perpendicular to the base, so this is great. But there's one flaw about it. We don't know the magnitude We don't know the magnitude of it. Like, yeah. So, okay, what do we do? Well, I'm going to draw it in such a simple word. So let's think about it. If I break everything apart, and let's say, because I know this here, I'm going to write it in nicer. Because remember, it's a direction. We don't know the unit, like how many units it is. So I'm just going to draw it really large, like that. Something like this. Let's consider that as the n vector. And can you see how it's still perpendicular to the base? This is great. So like that. Okay. There it is. So this is, yep, can you see how it's perpendicular to the base? If I can look at this and be, okay, so this is what I want. I want from here, from the base of the peak to the P. So look, the height. This is your height. The red part is the height, but of course, n is just the, can you see how n is just it's the directional vector. It's just direction. Can you see? But I want this height over here. And I'm just going to draw this here. I'm going to draw this part here because you know how from here to here, they are, of course, this is perpendicular. And I'm going to draw this part here, from here to here, AP, you know, in this nice orange color. So I'm going to draw this nicely here. So, because I want to explain what we have to do here. So I'm going to draw this big N here. This is your directional vector. I'm going to represent this in much more nicer. So imagine this is your directional vector. And of course, we have some part that's red here. You remember from here to here, somewhere around here? This is what we want. This is our height, yeah? This is the height. Same case as this, like that. Where, of course, this here is P, by the way. And from the red to, and it becomes this, so we got that, perfect. So we got P. And P, it looks like this, basically. So we have this orange color, which goes like this, basically. And it looks like that. Which looks like this. A P, and this is A here. This is A. So, okay. And then, of course, from here to here. It's a little bit supposed to be nicer, but this is supposed to look like this, by the way. Let's draw it like that. Okay, so this is where they kind of meet. And so, of course, this is your... Can you see how everything makes sense? So, you've got this here. Basically, it represents this part over here. Can you see how it's... Because can you see how... Why do I know they have to be perpendicular? Can you see how they're perpendicular, like the way we said it? So, they must be perpendicular. And this vector, yep, AP. We know what it is. So, okay, we know that's that. So, you know what are we trying to find? Can you see how this here... Isn't it just a vector resolute? Can you see how... Remember what a vector resolute is there? Imagine this here. Imagine this P to A. Imagine P to A, like P to A. So this is the directional vector. So it's basically P to A is casting a shadow on the vector N. Can you see? And it's casting this shadow. This shadow, the magnitude of it is called the scalar resolute. And that's what we want. Isn't it that red part, our height? That's what it is. It's that scalar resolute. So remember how to find the scalar resolute. It's just your, in this case, it's, you know, normally, no, this one is PA, dot product of PA times, your directional vector, which is, you know, of course, n, all divided by the absolute value of n. So there it is. Because do you know how this one's... So PA is casting a shadow on n, and it's creating this nice... Yeah, it's this... Yeah, the red part is your scalar resolute. So, yeah, so this is really good. So what we can do is go to our CAS and define some stuff. And write this expression, find the scalar resolute, by the way. So let's do that. So first what I'm going to do is first define n, because I haven't actually defined n. You remember n is this vector, so let's go to our CAS. N is defined as 6, 2, 5. So wait, 6, 2, 5. Okay, so that's, yep, your n vector, and let's write what we had to. So remember that, what is PA? PA is just negative P plus A. That's what PA is. This is your PA. So we're trying to find, let's write it down. So we're trying to find the dot product of, so matrix, vectors, the dot product of negative PA, comma, n. And then we're going to find the absolute value of n, which is not n. Ooh, why is it negative? Just make a positive. Remember, scalar is, it's just distance. So make a positive. I don't know why it's negative. Okay. Oh, yep, make it positive. There it is. So this here is actually our height. It's that red part. So let's go back to our CAS. So let's go back to our paper. So we found that this part over here, we found the actual red part, which is our height. So we found our height. So we can go back to our question. And now we've got the height. I'm being honest with you. This is a really hard question. That's what I'm saying. It was a really hard paper, this one. Root 65 over 65. And so now we can put this in our CAS and solve it. So 1/3 times, 2 root 65 times this expression here, which gives me 24. So the volume is 24 units cubed. Done. All right. Next question. Oh yeah, question 5 is out of the study design, so we don't even have to do it. It's mechanics. I'm sad they took it out, but yeah. So we can skip those. Question 6, which is the last question, which is probability. Nice. Let's have a try at this. So it says, a company produces packets of noodles. It is known from past experience that the mass of the packet of noodles produced by one of the company's machine is normally distributed with a mean of this and a standard deviation of 15. To check the operation of the machine after some repairs, the company's quality control employees select 2 independent random samples of 50 packets and calculate the mean mass of the 2 independent calculate the mean mass of the 50 packets for each random sample. Assume that the machine is working properly. Find the probability that at least one of those random samples will have a mean mass between 370 grams to 375 grams. Give your answer correctly. So, okay, not too bad. So what I'm going to first do is, okay, I'm going to normally distribute the sample mean. So, where it's normally distributed. So remember how the mean is the same as the original mean, which is 375, but your standard deviation of your mean, of your sample mean, is going to be of course S over root n. So what's my S? What's my standard deviation? My original standard deviation, my population standard deviation, it's 15 to the square root of n. And n, how many packets did we run? So we have, all the samples have 50, so 50 packets. So 50, which is basically 25 times 2. If you think about it, it's just, so 5 root 2 basically. Because 25 times 3 is 50, and these 5s can cancel. How many? So this goes into what, 3 times. There it is. So basically you can write it as 3 root 2 squared. That's your, okay. So now we've kind of got that. So, okay, so this is what we want to do. First, let's calculate the mean mass between these here. What's the probability of getting a mean mass of this? Easy. So we're just trying to find the probability that we need to get a mean mass from 370 less or equal to your sample x less or equal to 375. And then what's that equal to? We're going to use our CAS here. So I'm going to control N this whole thing here. Okay, so first, I'm just going to what's 3 over root 2, my standard deviation, in terms of control enter, get this number. Yep. So first, I'm going to go to probability distributions. I'm going to go to normal CDF. So 370 to 375. Your mean is 375, and your standard deviation is what we got here. And enter. And we get this nice part here. So let's write that down. That's the probability of getting between packets from 370 to 375 grams. So 0.49 basically, close. So, okay, that's the probability. But remember, there's 2 samples. We have 2 independent random samples. And what we want to find is the probability that at least one of those random samples will have a mean mass between that probability. So now we're dealing with binomial. Let's call y, binomially distributed. Y is the number of those packets. So there's 2 packets, of course. And what's the probability of a packet being between 370 to 375? Of course, it's this over here. That's the probability of success. So what we're overall trying to find is the probability, find the probability that at least one. So at least one is that blah, blah, blah. And you have to kind of find this now. So let's use our CAS here. So I'm going to control C this, probability, go menu, probability, distributions, binomial CDF. So n, of course, is 375. So what am I doing? Yeah, there's 2 samples. What am I doing? 2 probability of success is that. Lower bound is we're going 1 to 2. Enter, and that's your probability. So to how many decimal places? We want it to 3 decimal places, which is 0.741. Done. There it is. Next question. Assume that the machine is working properly. So working properly. Find the probability that the means of the 2 random samples differ by less than 2 grams. Give your answer to this. So basically, let's say, okay, those 2 random samples, which let's call them, let's call the first random sample as x1. And let's call the second random sample x2. So the difference is, of course, x1 minus x2. And we want the difference, this is called the difference, and we want it to be less Less than 2, yeah, less than 2. Less than 2. Now be careful. It could have been vice versa. It could have been that x2 minus x1. So there are two cases. Can you see how there's two cases? It's not always just one case. There's always two cases. It's x1 minus x2, the difference between them, or it could have been x2 minus x1. Those could have been a big difference, yeah. So we get this, we need a little bit simplify this. So kind of think of it like this. If I take a negative out here, doesn't it just become, then x1 minus x2? Like that, if I took that negative out. And if I divide both sides by negative, it doesn't just, become positive, because remember, an inequality changes, and this becomes -2 there. See how it changes? And now we get, these are the same, basically. Can you see how now these are the same? Yep. So what we're saying is this here, let's call D the difference. Let's consider D to be the difference. D is basically just x1 minus x2, the difference between this random sample. So these are the difference. So we're saying, hey, basically we're saying, hey, this D value, so this part here, let's rub those out. Let's consider that as D. So basically, like that. The D value must be less than 2, but it also has to be basically greater than 2. So the D value simplifies to be basically, it has to be less than 2, but it also has to be greater than 2. So the D value must be between -2 to 2. Yep, that's what we basically are trying to find the probability of, basically. So assuming that the machine was working, find the probability that the mean of the two masses differ by less than this. So basically we're trying to find the probability of this. Okay. Now, there's a big problem. We don't, the D, the difference. We need to find, of course, the expected value and the standard deviation, because we're using normal distribution here. So how do we do that? Well, we need to find the mean of D. So the mean of D is just basically finding, so the expected value of x1 minus x2, which is going to simplify to the expected value of x1 minus the expected value of x2. And these, because how they have the same mean, like, can you see how both have the same mean, like 375? It will be like 375 minus 375, which is 0. So the mean is 0, actually. So basically this part here, the expected value of D is 0. What about the variance? We also need to find the variance so we can find the standard deviation. The variance of this expression, so D, which is x1 minus x2, is what? Remember, the variance is a little bit different. So it'll be var of x1 plus var of minus x2. And remember, that minus is just a constant, like -1. If you take it out, take a constant out, it gets squared, which becomes positive. It becomes positive. So you know how x1 and x2 are the same? Like, they have the same variance. They would have, of course, the same variance. Because, they're the same thing. This is going to be added up. It's just the same as basically like 2 times. It's just going to be 2 times this over here. And the variance of x1, or, it doesn't matter because x1 and x2 are basically the same. The variance is this over here, which is 3√2 all squared. Because remember, it has to be squared because the inside standard deviation, yep. And that's going to be what? So let's go to our CAS. So it's 2 times 3√2 all squared. Done. So it's 9. But remember, that's your variance. Of course, we want the standard deviation. The variance is really useful. So standard deviation, just take the square root of 9. It's 3. So it's actually, overall, your standard deviation of D, I'll rub this out. Your standard deviation of D is actually just equal to 3. So now we can actually say D is normally distributed with an expected value of 0 and the standard deviation of 3 squared. And now we can actually use that to calculate this expression here. Beautiful. So to calculate this expression here, let's use our CAS now. So menu, probability, distribution, normal CDF. So we're going from -2 to 2. The mean is 0 and your standard deviation is 3. Enter. This is your probability. So let's write that down. To how many? 3 decimal places. 0.495. Done. Okay. Next question. To test whether the machine is working properly after repairs and it still produces, producing packets with a mean of 375, the 2 random samples are combined now with a mean mass of 100 packets is found to be 372 grams. Okay, assume that the standard deviation of the mass of the packets produced is still 15. A 2-tailed test at 5 levels of significance is to be carried out. Write down the suitable hypothesis, so the null and the alternative. This is really easy. We are doing a 2-tailed statistical test. So your of course, your null hypothesis is that there was no change. So your mean was just that 375 didn't change. And of course, your alternative hypothesis is when there's a difference. There's some difference that it could have been an increase in the mass, or it could have been a decrease. So which is, of course, not equal to that 375. Done. Find the p-value for the test. Really easy. For a two-tailed test, if you kind of draw a diagram, this is what it looks like. So if I draw a normal distribution, this is what it looks like. Because this is your x bar. Okay, so of course the mean is 375. You remember your p-value is when you're saying, hey, I accept the null hypothesis, but I'm trying to find out, what is the, So what is it? 372. 372. So 372 is here. 72 is right over here. Yep, so, and you remember a two-tailed test, it's two tails. There's two tails. This is one tail. And imagine, what's the difference? You remember, it's symmetrical. So 372, 375, this has to be 370. The difference is 3, so 5, 6, 7, 8, 378. Because there could have been an increase. Here it is. This is what the p-value is. It's the addition of these two here. That's your p-value. And because they're symmetrical, we know because they are symmetrical, all we're just trying to find, your p-value is just, imagine, find the probability that x bar is less than this one, 372. Yep. You're finding the probability, of course, given that the mean is, of course, 375, but you're doubling it. Remember, you're doubling because you know how it's symmetrical. This part here is symmetrical to that part, so we're doubling it. So which will give me, and by the way, any value here, if you have any value of your sample mean here, then we, of course, these parts over here and these parts over here are where we, of course, reject the null hypothesis. And there is actually enough evidence to suggest that there was some error, something's wrong with it. It's not working properly. So let's find, the p-hat. So menu, okay. Sorry. I just fully forgot. Wait. The mean mass of 100 packets. There's a big change also. They changed the n value, so that your standard deviation will change. So let's also consider that to be the case. Wait. So you know how the standard deviation is, of course, standard deviation for the sample mean is your original, which is 15, divided by the square root of, now it's going to be square root of 100, because now it's not 50, it's 100 packets, which is just 10, which is going to be equal to 3 on 2. So that's your standard deviation. Your new standard deviation is 1.5. So don't forget that. Actually, no, I forgot about that. So 1.5. Okay, so that's your new standard deviation. So let me just copy that. I don't want to. That's your probability distributions. Inverse. Okay, going negative infinity to 372. Your mean is the original 375, and your standard deviation is 1.5. Enter, and this is what we get. Of course, remember what we said, we double it, so 2 times that value here, and control enter, and this is your p-value, which to 3 decimal places 0.046 basically. Let's write that down. 0.046. Done. Next question. Does the mean mass of the sample of 100 packets suggest that the machine is working properly at 5% level of significance for a two-tailed test? Okay, easy. We know that if your p-value is less than the significance levels, which is 0.05, then we reject the null hypothesis. Remember, so when p is less than your level of significance, which is 0.05 in this case, we reject null hypothesis. It means that it is not working properly, so we accept an alternative. But if your p-value is greater than 0.05, we accept the null hypothesis. In this case, is our p-value less than 0.05? It is actually. You can see that the p-value is actually less than 0.05, which means that we can reject the null hypothesis. It means that it's working properly, and it's actually not working properly. There's evidence here that it's not working properly. So we can say p-value is less than 0.05. We reject null hypothesis. Hence, the machine is not working properly. Not working properly. Next question. What is the smallest value of the mean mass of a sample of 100 packets for the null hypothesis to not be rejected? In this case, our one right now, we rejected the null hypothesis, but now we want to find out what is the smallest mean mass for it to not be rejected. And that's easy. Like what we said, if it's around here, if it's around here and here, we reject, like what we said, if your sample mean is around those, we reject null hypothesis. But in this case, we want to accept it, mean that it has to be around here in the mid, this part here. And we want the smallest. The smallest, of course, would occur somewhere around here. Somewhere around here. Well, it's really easy because kind of think of it like this. How do I find that smallest part? If I know that, this here, because, level of significance, these parts here, these two here, it has to be, because it's symmetrical, this has to be, because of the 5% level of significance, this has to be 0.025. And this also has to be 0.025 because they, of course, have to add up to that 0.05 to, 5% level of significance. So if I know that this probability here is 0.05, let's call this XC, some value here, XC bar, let's call this, we didn't know what this was, let's say we didn't know what this was, of course, but now we're trying to find the smallest, so it should be around that 372 anyway, but XC, something like that. So this will give me, this is the smallest mean mass that we should not reject it. So so we want to find the probability that your X is less than XC, the smallest XC. Of course, accepting that, given of course your normal mean is 375, and that's going to be equal to 0.025. So that is nice. So let's do that. Now I just want to make sure. No, so I just want to make sure something. My standard deviations here. Okay, so what I'm going to do is menu. I'll go to probability distributions, inverse normal, because remember we're finding. So we got the error is 0.025. Your mean is 375, and your standard deviation is 1.5. Okay, and this is it. So to how many decimals? Of course, it's close to 372, but to one decimal place, it's 372.1. So your XC value, so sample me, the smallest for it to not be rejected is 372.1. There it is. That is it. I hope this video found you well. I hope, it helped you understand this. But it was a really hard paper. I'm not going to lie. It's a really, really hard paper. Good luck with your studies, and I hope this, helped you in your studies. Have a great day, guys. Bye-bye.